Previously, we had seen that when light impinges on a surface, some of the light reflects, which we took a look at in the previous few videos, and some of it transmits on through, or we'll say refracts. To get started here, the first thing I will need to do is define a quantity called the index of refraction. It's usually just written as n, and is defined as the speed of light in a vacuum over the speed of light in the medium. So light, when it travels through something that isn't a vacuum, travels more slowly. Now what's really happening is the atoms and molecules in the medium their electron clouds are acting like little antennas, and they sort of do a whole absorb and re-radiate kind of thing. So kind of acting like, a blocker in football or something like that, slowing up the progress of the wave. So light waves always travel at the speed of light in a vacuum, c. But in a medium, this effect of basically being absorbed and re-emitted and absorbed and retransmitted and whatnot adds delays to it. And so we usually say that the light travels slower in the medium. That's truly an effective speed, but that works for us. So anyway, this is meters per second. That's meters per second. So this index of refraction is just a number. It doesn't have any units at all. Also, this number is going to be equal to 1 if it's a vacuum, and it'll be greater than 1 if it's not a vacuum, because you'll be going slower than the speed of light in a vacuum. Now, the index of refraction for air is just minusculely greater than 1, so we can usually get away with approximating it as 1. This does have a side effect. If you remember from the study of mechanical waves, if a wave moves from one region where it's propagating at one speed to another region where it's propagating at another speed, the frequency of the wave stays the same, but the wavelength is what changes. So this actually gives us kind of a handy use for the index of refraction here. So let's say that we had light traveling in a vacuum. In a vacuum, we would say that the speed of light in a vacuum is equal to the frequency times the wavelength in a vacuum. And then similarly, we would say that in some medium, it would be equal to the speed of light in that medium, which is slower, will be equal to the frequency times the wavelength in the material. So we can equate the frequencies. So here the frequency for the in a vacuum we could write as the speed of light in a vacuum over the wavelength in a vacuum. And similarly, the frequency in the material we would write as the speed of light in the material over the wavelength in the material. Rearranging, this gives us that the wavelength in the material is equal to the speed of light in the material over the speed of light in a vacuum times the wavelength in a vacuum. But that is 1 over the index of refraction. So this gets used a lot to figure out how wavelengths change as things go into a material. So we can finally write that the wavelength in the material is equal to the wavelength in vacuum over the index of refraction. So that's a useful relation. Now, there are plenty of exceptions here. As a general rule of thumb, the denser some medium is, the higher its index of refraction will be. So in these videos here, we'll take a look at what happens when light transfers from one medium to another. So what you're seeing here is a half cylinder of lucite that's on a turntable that I can turn around. You can see that I've got a thin beam of light coming into the lucite. It will strike this surface here, and then we'll see how it refracts in just a moment when we turn the light. So you can see the light is coming in here right along the normal to strike this surface. That means there's an angle of incidence of 0 degrees, and so it just passes right out at an angle of refraction of 0 degrees. Now, since the index of refraction of the lucite is greater than 1, as we turn this, we can see that as the angle of incidence increases, so does the angle of refraction, but not as much. So the light is bending towards the normal on the way out. Notice too, as we get to steeper and steeper angles, that the reflected ray of light here is getting brighter and brighter. So here I've reversed the orientation of our half cylinder. Now notice here that when the light impinges on this surface here, it's always going to come in at the local normal to the surface. So this means that it'll pass through undeflected at this surface, and all the refraction will happen at this surface here. So here you can see as we increase the angle of incidence, the angle of refraction is increasing. And it's also the case that, like before, the reflected ray is getting more intense. But now notice here, remember all the refraction is happening at the flat surface here because we're always incident to the normal on the cylindrical part. Something's got to give, because since air has a lower index of refraction than the lucite, the angle that we make with respect to the normal is bigger than the angle of incidence. So, but the problem is that it can't get any bigger than 90 degrees, right? So, but there'd still be plenty of room on our incidence side to go to what the critical angle that would require that, and in fact beyond. So what happens when we get to that point? Pause the video and get back with me. Okay, so notice here as we approach the critical angle, which is the angle of incidence for which the angle of refraction would be 90 degrees, the intensity of the reflected ray increases and the refracted ray is decreasing. And at the critical angle, the intensity of the refracted ray goes to 0, and all we have happen from that critical angle on is reflection. This is a phenomenon known as total internal reflection. All right, so what you saw there was refraction. So here's our interface here. Let's just say this is air and this is glass for the moment, just to make it a little more concrete. We'll go ahead and erect our normal here. Remember, we always measure angles in optics with respect to the normal. So this is our angle of incidence here. This is our incident ray here, and this is our angle of incidence. And we did see from the video that the ray will reflect back out. There we go. Will reflect back out at an angle of reflection equal to the angle of incidence. Now, we will also call this theta 1. This will say that this is medium number 1 with index of refraction 1. And this is medium number 2 with index of refraction 2. We saw that light also would transit into the medium. And here where we're going into the medium, we're going from a lower to a higher index. And what we saw was that we bent towards the normal. So now the refraction, as you saw in the video as well, only happens at the boundary. It doesn't happen at any other point. Now, the relation between the angles is given by Snell's law. And this says that n1 sine theta 1 is equal to n2 sine theta 2. So here where n2 is bigger, we're going to need sine theta 2 to be smaller, which means that theta 2 will be smaller. So if you're going from a low index to a high index, you'll bend towards the normal. Similarly, if you go from a high index to a low index, you'll bend away from the normal. So again, we can prove Snell's law here using Huygens principle. So here's the boundary between my materials. We'll say that this is of index n1. This is index n2. And so let's say we have our incident ray coming in, like so. We'll go ahead, erect a normal, just like before. There we go. And we'll extend it down there. All right. So we'll go ahead and say that this incident angle here is theta 1. And this refracted angle here is theta 2. So again, just like we did with the law of reflection, what we'll go ahead and do is we will go ahead and erect a wavefront. So remember, the ray is perpendicular to the wavefront. So here I'm dropping a perpendicular here. And again, we're going to pick 2 points. We're going to pick the point right where the wavefront is intersecting with the medium. And we'll pick some other point over here. And so what we're going to do is we're going to watch both the wavelet that gets emitted here and the wavelet that gets emitted here propagate for the same amount of time, delta t. So some amount of time, delta t later, this wavelet from here made it to here. But this wavelet here, since the way I've got this drawn, n2 is bigger than n1, meaning that the speed of light in this medium is slower than the speed of light in this medium. The wavelet emitted from here won't have had as far to travel. Okay. So then we can go ahead and mark off those distances there. So this distance here is going to be v1 delta t, where v1 is the speed of light in medium number 1. And similarly here, this distance right here, there we go, is v2 delta t. All right. And we can go ahead, draw in our wavefront here. And again, that will be perpendicular to the refracted ray. So now here we're going to be considering two triangles, but we can't do similar triangles like we did for the law of reflection. So this triangle we're going to take a look at right here, and then the other triangle we're going to take a look at will be, this triangle right here. Now what they do have in common, at least, is they do have a shared hypotenuse. Now, we've already worked out before that this angle theta 1 here is also going to be this angle here. That will also be theta 1. And this angle theta 2 here, you can also argue will have to be equal to that angle there. So now what we can do is, by looking at this triangle here, we can observe that the sine of theta 1 will be equal to this leg here. This is the opposite, v1 over v1 delta t, and divided by whatever this hypotenuse is, which it won't matter because it's going to cancel. And that's because we're going to divide this by sine theta 2. And sine theta 2 is going to be the opposite here, which is v2 delta t over that same hypotenuse. So the small favors that we get out of this are that the hypotenusi cancel and the delta t's cancel. Now, by the definition of index of refraction, v1 is going to be the speed of light in a vacuum over n1, and this is going to be speed of light in a vacuum over n2. So again, more canceling. And when you cross multiply this out, you end up with sine theta 1 over sine theta 2 equals n2 over n1. Sorry, rationalizing the fraction here. Then when you cross multiply, you will get n1 sine theta 1 equals n2 sine theta 2. All right. So let's just do a couple quick examples of this. For instance, let's consider a ray of light in air that is impinging on crown glass. Now it turns out crown glass is one of two recipes of glass that are in wide use in optics. The other recipe of glass is widely used recipe of glass is flint glass. Of course, there are many, many other recipes for specialty uses, but for, say, camera lens design and stuff like that, you're going to see these two recipes used a lot. So here, the index in air, we are going to approximate as 1 because it's really close to that. And the index of refraction for crown glass is 1.523. All right. So let's say we have a ray impinging on a normal here. Ray impinging on the surface here, making an angle of 30 degrees with respect to the normal. Now we know we're going from a low index to a high index, so this means you are going to bend towards the normal. And I'd like to know what that angle is. So we can go ahead and do Snell's law on this. N1 sine theta 1 equals N2 sine theta 2. And so rearranged, and we get that the sine of theta 2 will be equal to N1 over N2 sine theta 1. So to get theta 2 by itself, we'll have to take the arc sine of both sides. So theta 2 will be the arc sine of n1 over n2 sine theta 1. So putting in our numbers here, this will be the arc sine of 1 over 1.523 sine 30, which is 19.2 degrees. All right. Let's revisit that same example. But let's say that for some reason, instead of being situated in air, our crown glass was situated in carbon disulfide, which I'm sure is something really horrendous, but it was just something I pulled out of a table to have an index of refraction that I wanted. All right. So here's our carbon disulfide. It has an index of 1.623, and then again we'll say that this is crown glass with an index of 1.523. So again, let's say that we come in at that same 30-degree angle. So theta 1 equals 30 degrees. Now here we're going from a higher index to a lower index. So this means we will bend away from the normal. So I'd like to know, what angle are we going to make with respect to the normal there? Well, fortunately, because we did this previous problem with letters, we realized that literally nothing changed except the numerical values that we put in. So this means that we can just go ahead and steal the result that we had from before. Copy. And paste. There we go. And substitute in the new numbers. So now we will be wanting to take the arc sine of 1.623 over 1.523 sine 30, which works out to be 32.2 degrees. Alrighty. So one of the other things that we saw in the video, though, was that as the angle got bigger and bigger, in this case here where we're going from a higher index to a lower index, we saw that as the incident angle got ever bigger, of course the angle of refraction would get ever bigger, but then this means that this angle is tending towards 90 degrees before this is ever going to get there. So it turns out, it's beyond the scope of this treatment to prove it, but as you saw in the demonstration, the intensity as we approach this critical angle, where the angle of refraction would have to be 90 degrees, it turns out that the intensity of the reflected light approaches 100%, and the intensity of the refracted light approaches 0%. And then if you go in an angle of incidence steeper than that critical angle, you would get, if you just blithely solve for it, you'll get that the angle of refraction is an imaginary number, which would make no sense physically. But again, the intensity of the refracted ray still works out to be 0. So it doesn't matter that the math gives you a nonsense answer. It's a physical situation that just isn't going to happen. So the phenomenon that you saw there is called total internal reflection. So if you're coming, oops, there we go. So if you're coming in at the critical angle, you would hypothetically be refracting out at 90 degrees, but the intensity of this light is 0 at that point. Again, reusing our result though, we can observe that that our critical angle, just reusing this result from before, we'll put in 90 degrees for sine theta 1. So we get that the critical angle would be the arc sine of n2 over n1 sine 90 degrees, but the sine 90 degrees is 1. So we get that the critical angle is the arc sine of n2 over n1. So if you come in at that angle or steeper, all the light will get reflected and stay inside. All the light will get reflected and stay inside this denser medium here. And none of it will go into the lower index medium. Now, I would submit that as a driver of late 20th and especially here in the early part of the 21st century, I would submit that this phenomenon is actually one of the single largest drivers of our current culture. Why is that? Pause the video and get back with me. Yeah, it's because this phenomenon is what's behind fiber optics. So this is the glass in the fiber. And so what happens in fiber optics is you send out a pulse of light going down your fiber optic, and the angles are always steep enough that they just totally internally reflect, and they just rattle back and forth within the fiber. This is the backbone of the internet. Pretty much as soon as you get to your internet service provider, everything goes fiber optic, including beneath the oceans to connect the continents. So without this, there would be no cat videos to enjoy. So just think on that one. Alrighty. So in the next video, we will take a look at dispersion and get into what's happening with rainbows. Catch you in the video.